This is the 7th section of chapter 2, and this section is on frameworks in equilibrium. So let's imagine that we've got a framework like this one here that's drawn, and it's suspended, let's say from 2 cables or 2 bits of string here. So we'll do those up like that, and we've got some sort of ceiling or some sort of place where it's hanging from. And those 2 bits of string or cable, we have tension in those, so we'll call those T1 and T2. And let's say we're required to work out what these tensions are. Well, we may well know, or we can work out the total weight of the framework, so we can resolve vertically and say that T1 plus T2 equals the weight of the network. Also, if we work out where the center of mass of the framework is, so I'll just put that here and we'll call that G, then what we can do is to take moments at a point either where T1 is or T2 is, and take moments from those points along with this center of mass and use that to write a moments equation, so we can then have a second equation in which we can then work out T1 and T2. Example 19. The inverted T-shaped uniform framework of weight W is shown in the diagram, is freely suspended from D and G by 2 vertical strings, so that AH is horizontal. So this is horizontal here. The 2 strings in the framework lie in the same plane. What we need to do is to find, in terms of W, the tensions T1 and T2. So we'll just add in that the weight is going vertically down. So the first equation that we can write down, if we resolve vertically like this, is that T1 plus T2 is equal to W. Now the next thing we need to do is we need to find the center of mass of the framework so that we can take moments. So we need to put this on some sort of coordinate grid. So what we'll do is we'll put AB on the y-axis and we'll put AH on the x-axis so that the origin is at the point A. Now, since this is a symmetrical shape, we can see it's symmetrical. This distance here is 6, so if that's 2 and that's 2, this length here has got to be 2, and this is 2 here. So this is symmetrical. So we can find x bar by symmetry. So the center of mass is going to be here. So x bar by symmetry is going to be 3. So we're now going to work out y bar. I'll just put in the lengths of these sides here. Now we know it's all symmetrical, but we'll put them in just to make sure that we don't miss any out on our working. And I'm just going to put like a little dot down where the center of mass of each one of these parts of the framework is going to be. Remember, with a framework, we take the center of each part of that framework as the center of mass, and we're going to take its length as its area in the working. Sorry, the length that we take that as the mass. So y bar is going to be the sum of each mass times by its center of mass in the y direction multiplied by the sum of the masses. So if we start with the part of the framework which is the line AB, so that's going to be 2 times by its center of mass in the y direction is going to be 1, because it's just going to be 1 unit up halfway between 0 and 2, plus then we'll take the part of the framework which is B to C, so that length is 2 and its center of mass is going to be a y coordinate of 2. Now it might be helpful actually if I just marked some numbers here, so that's going to be 2 there, and this will be 8 up here. Then I can work out this distance here, so I'll put all of them on actually. So that one will be 5 here. That center of mass we've already got there, that's going to be 1. So I've now got all of those y distances. Right, okay, so we're now on to CD. Now CD is a length of 6, its center of mass is 5. Then DE, length of 2, center of mass is 8, y coordinate of 8. Then EF, length 6, center of mass 5. FG, length 2, center of mass 2. And let's move this out of the way here. We're now on to GH, which is length of 2, center of mass 1, and then lastly HA or AH, length 6, center of mass 0. It's quite a long calculation, and we'll divide that by the sum of the masses, which is basically the sum of the lengths. So 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 2 plus 6. So that becomes 88 divided by 28, and that can simplify down to 22 over 7 divided both by 4. So now we know the position of the center of mass. So we'll just mark that in on the diagram. So we know the center of mass is along this line. 22 over 7 is just up 3 and a bit. So the center of mass is going to be somewhere around here. So we'll just take these other bits off the diagram. We don't need those at the moment. We'll just try and tidy this diagram up here, like that. So actually at that point where the center of mass is, that's where W is acting, and that will enable you to take moments. Now I could take moments either from T1 or T2, because I really want an equation without one of those so that I can eliminate it from this equation. So let's say, for example, I took moments from T1, so from this point here, okay, and my moments diagram is probably going to look something like this. So I'll need to know that distance to get to the perpendicular line of action where W is, and then I'm going to have a distance here to the tension T2. Okay, so I'll just draw that out of the side. So here's my T1, a distance to W, like that, and then another distance that takes me to T2 over here. Now I can fill those distances in, they're fairly easy to work out. Since the center of mass is along this line of symmetry, then that's just a 1 centimeter length, and then we want this distance here, so that's just going to be 2 plus 2, so that's going to be 4. So that distance from there to there is 4. So that's if I were to take moments about the point T1. I'm just going to show you what it would look like if I was to take moments about T2. So yeah, down here you see the moments equations if I took moments about T1. So we've got this distance here, which is going to be 3, then times by the weight, and then we've got this distance here to T1, so that's going to be a distance of 4 times by T1. So I'm going to do the working both ways with T1 and T2 so that we can see we get equivalent answers, but in reality you would just choose one or the other. So taking moments about T1, if I were to do it this way, I'd have 1 times by W, which is my clockwise moment, is going to equal to 4 times by T2, which is my anti-clockwise moment, so I've got 4T2. If I now substitute that into my forces equation here, I'm going to have T1 plus T2 is equal to W, which is 4T2. That means that T1 is equal to 3T2. So since I'm writing T1 and T2 in terms of W, so using this equation now, divide both sides by 4, I can say that T2 is equal to 1/4 W. And then by using this equation here, I know that T1 is going to be 3 times by T2, so 3 times by that is going to be T1 is equal to 3/4 W. So what I'm going to do now is basically check that I get the same solution if I use my moments equation about T2. Now my moments equation about T2, which is this one here, gives me 3W, which is my anti-clockwise moment, is going to equal to 4T1, which is my clockwise moment. So 3W is equal to 4T1. So straight away from this, I can get, if I divide both sides by 4, I will get T1 is 3W divided by 4, which is 3/4 W. I can then use this equation here, since I know what T1 is. So T1 is going to be 3/4 W. So T2 will equal W minus T1, or W minus 3/4 W, which gives me T2 equals 1/4 W. So you can see whichever place you take moments from, you'll get exactly the same answers, but it's best just to pick the place that's going to be the easiest for you. Okay, let's now move on to part B. Okay, so in part B, it says here the string breaks, or the string at D breaks. So that's going to be this string here is now gone. And the framework hangs freely in equilibrium from G. And part B, find the angle that DE makes with the vertical when the framework comes to rest in equilibrium. Okay, now it's going to look something like this, but you don't need to actually draw that diagram. What's important is that that center of mass needs to be directly below the point at which it's attached or freely suspended. So I just need to make sure on my diagram that I draw a line going through G through the center of mass, and I've put it on here, so I'll just maybe draw that a little bit more clean and draw it for you again. So center of mass going through the point that it's suspended, which is here, and then I'm going to be using some trigonometry to work out what that angle is. So I'll just tidy up those things a bit. Okay, now this is where I think the book is wrong, because it talks about the angles as if it's suspended from D, but that doesn't make sense because it said this string is actually broken, so I think there's a mistake there. And the actual angle that we do need to work out is going to be this line here, which is now the vertical, and DE. So this is the angle that we need to work out here. Now we only know this length here. We can work out this length by doing 8 minus 22 over 7, but we can't work out either these two lengths. But we do have a Z angle here. So if I work out this angle here, that angle, that's going to be the same as this one, and I've got enough information to work out the lengths of these sides. So we'll just draw out that triangle a little bit bigger here. So we've got triangle here. So this is where the weight center of mass is, W, sorry, it's at the top part of that triangle. So yeah, this is the point where W would be. This is the point G here at this end. Okay, and here's the vertical where W is. So what do we know? So the distance from G to that center of mass, so we know this side length is 3 because that's dead center here. Then we want to work out this length here. Now we know the length from the bottom to this part is 2, and the length from the bottom to this part is 22 over 7. So if you do 22 over 7 minus 2, we get this length here, which is this length here. So this length is 22 over 7 minus 2, and this is the angle that we need to work out. So all we need to do in part B to find the angle is we're going to do the tan inverse of 22 over 7 minus 2 over 3, opposite over adjacent. And that gives me 20.854, like that. And I want to give that to 3 significant figures. So we'll do 20.9 degrees to 3 significant figures. Now, in the version of the book I've got, it's got a completely different angle, but that's because they've worked out the angle as if it's suspended from D. Now, the version of the book you may have may be updated and have the correct answer, but based on my understanding of the question, the answer should be, to 3 significant figures, 20.9 degrees. Example 20. The inverted T-shaped uniform framework used in example 19 has mass W kg. So there's my uniform framework here from the previous example. And in part A, we need to find the location of the center of mass when a mass of a quarter W is fixed at a point H. So I've now got another mass here that has a mass of a quarter W. Now from before, I know that the center of mass was around about here. Well, it's just a little bit higher. We've got that from the previous example, around about here. And now we're calling the weight W. So let's put down the coordinates of these two masses. So this the mass from before, that was 322/7. That's its center of mass. And then for H, I can see its center of mass is at 60. So what I can do now is I just clump the whole framework from before into a single particle where its center of mass is, and use W as its mass. So I'm going to work out X bar and Y bar. So X bar, we've got the total mass of that system, or the weight of the system, times by its center of mass in the X direction, which is 3. Then we've got the quarter W weight or mass, and we're going to multiply that by its center of mass in the X direction, which is 6. And then we add together the total masses. So all of the W's are going to cancel out like this. And what we'll have is 9/2 divided by 5/4. And that gives me 18/5. And that's 3.6. We'll do the same for Y bar now. So we'll take the mass of each part. So the framework, mass of the framework is W. Its center of mass in the Y direction is 22/7, plus the mass that's been added times by its center of mass in the Y direction, which is 0. And we divide that by the total masses. So just like before, the W's are going to cancel out. So that will give us 22/7 divided by 5/4. And that gives us 88/35. That doesn't give us a nice decimal, so we'll just leave it as 88/35 there. So we have our X bar and Y bar. Right, okay, part B. Find the angle that D makes with the vertical when the system is freely suspended from E. So we can take these masses off because we've now got a new center of mass in it. That is 3.6 across, so it's moved slightly across from the 3, and 88/35 is about 2.5 something, I think, something like that. So it was 22/7, so it's moved up slightly, so it's moved across to the right slightly, and it's moved actually no, it's moved down slightly, because 22/7 is a little bit more than 3, so it's moved to the right and it's moved down slightly, which is what we'd expect. If we add a mass here, that's going to have an effect on the whole system. It's going to move the whole center of mass towards it, and that means moving across and move down. So let's just mark roughly where this new center of mass is. So it's going to be sort of in this place here. So let's call that G, and we want to find out the angle that DE makes with the vertical. So we need to draw a line going from the center of mass through the point E. So that's going to be a line something like this, and the angle that I need to work out is going to be this one here, because the green line is now the vertical. So I'm just going to draw that into a bigger right angle triangle. If I sort of just draw the dotted line on, this is where my right angle triangle is going to be, and the angle that I need to work out is this one here. So I need the lengths of those sides. Now, if I want to find this vertical side here, I know that the total distance from the bottom to the top is 8. And I know that the distance from here to the centre of mass is 88 over 35. So if I do 8 minus 88 over 35, I've got the length of this side here. So I'll write that down. 8 minus 88 over 35. Now for this little distance here, well, let's mark on. I know that this distance is 3.6. That means that the distance on this side, because it's all got to add up to 6, it's got to be 2.4. So this distance between those two is 2.4. Now I know that this distance is 2, which means that this little distance here must be 0.4. So 2.4 minus the 2 that's there. So that little length at the top is going to be 0.4. So now we'll do the tan inverse of the opposite, which is that 8 minus 88 over 35 divided by the adjacent, which is 0.4. And if we do that, we're going to get 85.829 degrees. So to 3 significant figures, we'll give it as 85.8 degrees. And again, just like the previous question, I do not agree with the working that's in the book. They've worked out this length here, which is this length here, as 6 minus 18 over 5, which is 2.4, which doesn't make any sense. How can that length be longer than that side here? It doesn't work. So by my understanding of the question, I've got 85.8 degrees, and that's to 3 significant figures. So you should now be able to complete exercise 3G on pages 60, 60 to 68. So on these types of questions, 2 things we want to do is we want to resolve vertically, and we want to take moments, and it would make sense to take moments at one of the points where you have tension, so that you can eliminate tension from your equations.